we will be talking about linear phase FIR filters. To begin with, we need to know what a linear phase is. Linear phase is the property of the filter where the phase response of the filter is a linear function of frequency, as a result of which the frequency components that would pass through the filter would face a delay by the same constant amount, which is referred to as the group delay, or we can say the group delay will be always a constant term in case of a linear phase filter. That is, all the frequency components that would pass through the filter will face the same amount of constant delay. The consequent of which is that there will be no phase distortion due to the time delay of frequencies relative to one another. As there is no distortion, it is very useful or is a boom for communication engineers. And for discrete time signals, perfect or exact linear phase is easily achieved with a finite impulse response filter by having coefficients which are symmetric or antisymmetric. The first criteria for a linear phase filter would be the impulse response is either symmetric or antisymmetric, that is Hn is equal to plus minus h of n minus n, where the length of the filter is capital N plus 1. Here there can be 4 cases depending upon the conditions of Hn and the length. Hn can be symmetric and antisymmetric, whereas length can be either odd or even. So there can be 4 cases, that is Hn symmetric, odd length, Hn symmetric, even length. Then again Hn antisymmetric, odd length, and Hn antisymmetric, even length. The type 1 is where the impulse response is symmetric and the length is odd, that is capital N is even. Say for example, if we take capital N as 8, then H0 is equal to H8, H1 is equal to H7, H of 2 is equal to H of 6, H of 3 is equal to H of 5, and H4 is a loner. It doesn't have any pair. Now, if we want to write the H of Z, then we can write H0 plus H1Z inverse plus H2Z to the power minus 2 plus H3Z to the power minus 3 plus H4Z to the power minus 4. Now H3 is again equal to H5. We have written H of N as H of suffix N for convenient purpose. Now H of 3 is again equal to H of 5. So we can write H of 3 plus H of 3Z to the power minus 3 plus H of 3Z to the power minus 5. Now H2 is same as H6. So H2Z to the power minus 2 plus H2Z to the power minus 6. H1Z to the power minus 1 plus H1Z to the power minus 7, as H1 is equal to H7. In this way we have written the Hz. Now if we replace z by e to the power j omega, and so here we can write as follows by utilizing the Euler's equation. Here, if this is the equation, then the in general equation that we can write for type 1 linear phase FIR filter would be H e to the power j omega is equal to e to the power j omega. It was 4, so it can be written as n by 2 because we started with n as 8, and the rest is written as H tilde omega, where H tilde omega is H of n by 2 plus twice summation n going from 1 to n by 2, H of n by 2 minus n into cos of n omega. You can put the different values of n and you can see we will get this equation back if we take capital N as 8. This equation is particularly for n is equal to 8. Here we have written the in general equation. Now h tilde omega is called the pseudo magnitude. Why pseudo magnitude? Because it is not only the magnitude, but it will have some part phase also. Now here phase would be equal to minus 4 omega plus beta, which is for the pseudo magnitude part. Now the group delay, which is defined as minus of d phi d omega, is equal to 4, which is constant. Or we can say for a type 1 linear phase FIR filter, the group delay is n by 2. The group delay as here shown here is defined as minus d phi d omega, where phi is the phase. So in general we can write the group delay as always for type 1 as n by 2, which is a constant. If n is constant, then n by 2 would also be constant, which shows we can achieve exact linear phase. Now from here, if we take Z transform on both the sides, we can write Hz from the first equation from where we started. If we take Z transform on both the sides, what we get is Z to the power minus n h of Z inverse. So here if we take, as n is even, if we take Z as 1, what we get is